Hey students, God, is this stuff crazy or what? I've been going nuts trying to get these stupid videos to work because I'm not the most technologically sophisticated person in the world, as Daryl and my flip phone, which he thinks is so awful, will attest to. Okay, so I'm trying to figure out how to make this work, and my stinking laptop sometimes isn't recording what it's supposed to be. It's driving me nuts. But anyhow, hopefully this recording is working. All right, and I'm going to address some of the questions that you all sent me. Okay, so one thing is like, what's a solenoid? What's a solenoid versus a relay? Okay, so a solenoid. Another related question: does every electric current generate a magnetic field? And therefore, if it does generate a magnetic field, does that mean that all electric circuits have magnetic fields? Okay, so you take a wire, you run current through it. It produces a magnetic field according to the right-hand rule. In other words, if the current's going this way through the wire, that way, then the magnetic field wraps around the wire like this. Okay, so you have this spiral of magnetic field around this wire. The answer to the question of does this mean that every electric circuit has a magnetic field? The answer is yes. Every electric circuit in which current is running, which charge is moving through it. So obviously, if we turn this circuit off, or some other situation occurs where there's no electric current going through the circuit, then there would not be a magnetic field. But if there is electric current going through the circuit, then there is going to be magnetic field. So yes, all electric circuits produce magnetic fields. And this is the thing that people need to remember, is that an electric circuit, because it generates a magnetic field, it affects the world around it. Okay, so an electric circuit generates a magnetic field, and in theory, that magnetic field goes out forever. Okay, now its strength drops off rapidly as it goes, but every electric circuit affects the world around it, or at least generates a magnetic field that could potentially affect the world around it. Now, you take this wire and you wrap it into a loop, and now I have folded that spiral of magnetic field around onto itself. I've made it stronger. If I take the loop, make a bigger loop of wire like that, that is a coil. That's a solenoid, basically. Very crude one, but that's a solenoid. Okay. More wraps, more concentration of the field. Make more, you make still more concentration of it, and this produces an electromagnet. A solenoid is essentially an electromagnet. If you put material inside the solenoid, then you can affect the magnetic field. So a solenoid that's just air like this, okay, is one thing. If you put a piece of wood in it, a piece of plastic, or a piece of some other non-metallic material, by and large, that material doesn't affect the magnetic field much at all. If you put a piece of copper or aluminum, certain metals have some effect on magnetic fields. You can get some strengthening or even weakening of the field, depending on what the material is. This has to do with whether things are paramagnetic or diamagnetic, material properties. The thing that really makes a difference is an iron material, a ferrous material, because in a ferrous material, the atoms, the domains inside the metal, the metal just likes to form magnets, and you put it inside a solenoid, and the solenoid will align all these domains. And I'm hearing that my battery is running low, so I'm going to pause this video. Okay, so anyhow, iron material will strengthen the magnetic field of the solenoid, and it will form its own magnetic field, so you can magnetize ferrous materials. Okay, materials that are iron or have properties similar to iron. So that's a solenoid, an electromagnet. And then what's a relay? Well, a relay is typically a coil of wire, a solenoid, that with a piece of iron that's like outside of it, when it turns on, it creates a magnetic field and pulls that rod inside, okay, so that the relay starts to activate a switch. Okay, in your car, for example, and I'm going to show videos here in a minute. Hopefully it works and you all can see them. But in your car, for example, when you turn your ignition key, activate the starter, and the car starts. Okay, if it's not electric car. Well, when you're turning that key, that switch at the ignition switch, that switch is not connected into the big fat cable that runs from the battery down to the starter. You don't get all that. There's like 100 amps of current or so that flow through that cable when you turn on the starter motor. No, okay, that what is your ignition switch turns on a switch which turns on a solenoid. Okay, runs current through a coil of wire, an electromagnet, and that then pulls a plunger in, and that pulling action of the plunger causes a switch to connect. Okay, so that plunger activates a switch that is in the big fat battery cable. Okay, so that's a relay. This is why when your car's battery is really low and you turn the key, you get a click. Okay, the click is that the solenoid activating, meaning that the battery can generate enough current to energize the solenoid and cause it to do its thing, close the switch, but it does not have enough, cannot generate enough current to actually run the starter motor. So it energizes the solenoid, you hear the click, but it can't actually turn the starter. All right, so that's a solenoid. Let me show a couple things. I'll pause this for a minute, and then I'll turn off the lights, and I'll show you a couple things on video. Okay, so in this video, we have somebody has created a solenoid. I'm out of the way here a little bit. You see there's all this, looks like dust on here. These are iron filings. Just if you took a piece of metal and you just took a file and on a piece of iron, you sand off bits of metal. That's what that is. Lots and lots of little bits of metal. Okay, and then they have set this up to run electric current through it. So when they run an electric current through it, it'll turn on the magnetic field, and hopefully, okay. And so then they're going to turn on the magnetic field, and the magnetic field will cause all the little bits of iron to align with it. Now, if you're having trouble seeing this, go look on YouTube. That you can see they're coming up close. You can see how the little bits of filing are lined up. Go to YouTube, Google around for some stuff on solenoids and relays, and you'll see this stuff for yourself. It's better than looking at it the way I have it set. But here that you can see the iron filings have aligned up going through here. Down here, they're kind of like just randomly scattered about, but down through the center, they've aligned up, showing the magnetic field there. Now, so let me then switch to this video. Okay, now in this video, you see the person has created up here, there, okay, a coil of wire, wrapped a coil of wire around essentially a plastic tube. And then a nail is right here, and they're going to connect this up and create a magnetic field. This is a much tighter wound wire than what you saw in the previous video. And this will create a magnetic field, and then this is a nail, it's iron, it'll be pulled into the solenoid. Bing, there it goes. Ta-da! Now, that is the basis of a relay, okay? Because when you have that mechanical action, you can then have this end connected to a switch so that so this is like your car, you turn your ignition switch, it activates the coil, it pulls the metal bar in, and the metal bar is connected to another switch for your, that runs through the battery cable straight to the starter motor, and that throws that switch and activates your starter. So this is a simple home-built basic idea of a relay, right? Okay, pause it again. I'll turn the lights back on. Okay, another question that someone asked was, why do the lines of force go in a certain direction? Well, if you remember, if you looked at that video, the previous video, the one, that one, okay, there's not any arrows or anything that show what direction you're in. Nothing says this is north and that end over there is south, okay? These are conventions. Remember how we talked about that the flow of electric current that you had, like, you know, it didn't really matter whether you talked about positives going this way or negatives going that way. It's just that because of convention, this is how this has come to be. The same thing goes with magnetism. Okay, yes, magnetism is real. Yes, you get this, you know, you see these lines of force reflected in the iron filings. But which ends, why is one end north, one end south? Why did the line start at one end and end at the other end, or so on and so forth? And the answer is convention. When these phenomena were first discovered, people would find a natural magnet, cut a lodestone, and you could magnetize a needle, for example, and float it on a cork in a piece of water, and the thing would turn toward the north. This is the development of early compasses. And so you called the end that went toward the north end, and the end that pointed toward the south end. And that's where the terms come from. Okay, and then by convention, we have the arrows start and leave the north end and go to the south end. So it's convention. It describes a real thing, okay, real magnetic phenomenon, but the idea of which way does the arrows point, are they clockwise, are they counterclockwise, do they go out from the north, that is by people's conventions. The right-hand rule, that is a real phenomenon, real thing. Okay, it turns out it's not just in electricity that this right-hand rule shows up. If you've ever played with gyroscopes do all kinds of weird things. For example, the reason you can ride your bike and stay up on the bike is because of the gyroscopic effect of the wheels. If you stop going forward on the bike, you stop moving, you fall over. Okay, why? Because this is a physics thing. But just like a train has momentum, it's going down the track, it's hard to stop, okay? So, and a barge has momentum, it's going down the river, it's hard to make it stop. A spinning wheel has momentum too, and that momentum has a nature. It's hard to make a train stop or a barge stop. It's also hard to make a train turn, right? If you have a train that's going 60 miles an hour and then you have a sharp bend in the tracks, that train's not going to make the bend. It's going to go right through the track, okay? So likewise, with rotational momentum, it turns out it has a direction too, and it likes to stay in the direction it's in, and that's why the wheels on your bike stay up. Well, it turns out to understand all this, it involves the right-hand rule. So it's not just a magnetism thing; it's also in mechanics. So all these things, they describe real phenomena, but the exact choice of like that, you know, why does the line go from negative to positive? Why does it show us clockwise or counterclockwise on this diagram? That is more people's conventions. This video is going to be too long because I'm answering some questions too, but someone asked about hysteresis. So the hysteresis of a magnet. Let me flip out where this is. Okay. It says a magnetic material whereby a change in magnetization lags, L-A-G-S, the application of the magnetic field intensity. The field intensity can be readily increased or decreased, and can be reversed. Well, so when you magnetize, so if you put in this coil up here, if you put a nail or iron bar in there, you turned on the current, the nail would magnetize, okay? But it takes some doing, all right? It doesn't magnetize instantly, and you crank up the field, and that will raise the amount of magnetization in the bar, and you reduce the field, reduce the amount of magnetization. But the bar likes to be magnetized. In other words, once you magnetize it, it will reach a certain point and it will retain that magnetization. And if you want to like magnetize it the other direction, you have to like apply field to it. So there's like a resistance or a slowness to this process. This is part of this hysteresis curve that you apply a magnetic field, and then it will get a magnetic field, and then you apply it in the other direction, and it will get the field in the other direction. But there's sort of a lag effect. My goal here is to try to keep this under 45 minutes, and with the other questions and stuff, I think I better, the examples I want to do, I think I better stop. So anyhow, I hope this stuff helps, and this is no great way to run a class, let me tell you, but it's what we got.